The scientific revolution of the 17th century was one of the pivotal movements in the development of the modern world. While we should not view the 17th century movement as the only significant century of scientific discovery and progress, the discoveries, conclusions, and innovations of the 17th century were without question very formative and essential for future developments in science. There are many ways that we could date the scientific revolution. Indeed, some of its most formative discoveries were made in the 15th century as part of the Renaissance, and some of its most comprehensive conclusions were formulated in the 18th century. But the 17th century is a useful century to highlight as a century that seemed to be central to revolutionary discoveries and conclusions. The 17th century scientific revolution was generated by a multitude of causes. One of the foremost causes was a new attention and understanding of mathematics. Advanced algebraic and trigonometric equations, as well as the development of calculus, buttressed medieval understandings of math and made discovery possible and explainable. New inventions were also a significant cause of the revolution, including microscopes, telescopes, and improved laboratory procedures. Scientists and theorists from the ancient world were given new attention and a new respect to what they could offer toward scientific understanding. The Renaissance provided 17th century thinkers with long-lost or neglected classical manuscripts, as well as manuscripts from Arab sources in the Middle East that expanded existing knowledge. The theology of the Reformation discredited medieval Catholic superstition and brought a new emphasis to the priesthood of all believers, and therefore the primacy of one's intellect, individualism, and personal encounter with God and the universe. Removing the authority of the papacy created a power vacuum in which scientists could step into and test their theories. Surprisingly, theories of magic, and particularly alchemy, the ability to transform one element into another, or at least belief in these possibilities, spurred additional research and discovery and led to results that were not always expected, but nevertheless important. The printing revolution also was important for the sharing of data and the comparing of findings between various researchers. Perhaps the greatest revolution that was achieved in the 17th century in regards to science was a significant shift in man's view of his world that opened wide the door to many future discoveries. Before the scientific revolution, European conceptions of the universe were a mix of Greek conjecture and medieval superstition. Knowledge of matter, motion, and reactions were almost unknown. Many Europeans continued to view the world and universe through the lens provided by the medieval Roman Catholic Church that emphasized angels and demons and blessings and curses as more explanatory of the universe than natural laws and a systematic created order. The so-called new science that emerged in the 17th century emphasized observation, discovery, experiment, and measurement more than superstitious and supernatural forces. The realization that nature and the universe is governed by identifiable and measurable laws may be the revolution's most important contribution to modernity. Removing Greek suppositions and medieval subjectivism paved the way for objective analysis to become the hallmark of modern science. The emergence of inductive and deductive thinking would become the two pillars of what would become the scientific method, the essential tool for an infinite number of future scientific inquiries and conclusions. Essential for the development of scientific inquiry in the century was the formation of scientific societies where researchers and theorists could share and discuss the ideas and findings with other like-minded researchers. The first such scientific society was the Royal Society of London for Improving Natural Knowledge, founded in 1660. The Royal Society was granted a charter by King Charles II in 1662, which served to bring additional notoriety and legitimacy to the association. The Royal Society would become the premier scientific association of the 17th century and would showcase the works of some of the biggest names in science during that century. Other European monarchies would follow suit, chartering their own scientific societies in the decades to come. It is helpful to consider the research breakthroughs during this century by considering various fields of scientific inquiry, including physics, medicine, chemistry, and biology. Early scientists also developed a new philosophy of science as well that was essential for conducting future research. Much of the scientific revolution focused on the field of physics, particularly the study of mass, acceleration, motion, and forces. While early physicists certainly conducted their early experiments on Earth with small demonstrations, they were often primarily concerned with discerning the structure and nature of the universe. They sought to understand the relationship between the sun, Earth, and planets. The startling advances in the field of physics during the 17th century inaugurated a new and breathtaking understanding of the universe for the first time. For 5,000 years, the prevailing notion of the universe was that the Earth was the center and that all heavenly bodies had been placed in the universe in relationship to the Earth. In Aristotle's conception, the heavenly bodies of sun, moon, and stars were ethereal, heavenly, and perfect, comprised of substances different than the Earth. The Earth was physical and comprised of earth, water, fire, and air. The geocentric view placed man ostensibly at the center of the universe, and several Bible verses were interpreted necessarily to endorse the geocentric view. Many contemporaries rejected any theory that challenged the geocentric view as hostile to Aristotle and the authority of the Church. Medieval thinkers are often accused of believing the world to be flat, which is untrue. The spherical shape of the Earth had been understood for several thousand years, but most contemporaries did believe the Earth was the center of the universe. The German-Polish astronomer Nicholas Copernicus was not the first to challenge the geocentric view of the universe, but he was the most modern and the most articulate in advocating a new worldview. Copernicus was a brilliant polymath, a researcher in a multitude of fields, including astronomy, mathematics, physics, medicine, theology, and humanities. Copernicus employed his prodigious mathematical skills to prove on the basis of astronomical data that indeed, not the Earth, but rather the sun was the center of the universe. Copernicus compiled his data and mathematical proofs for a heliocentric view of the universe into his work on the revolutions of the celestial spheres. Copernicus's work was the first detailed and mathematically based argument for the heliocentric view. But Copernicus may have stalled publication of his work, fearing the backlash of the Catholic Church and his contemporaries. On the Revolutions of the Celestial Spheres was finally published shortly before Copernicus's death, and thereafter, as expected, did generate significant controversy in European universities and within the papacy itself. On the Revolution of the Celestial Spheres was the first comprehensive work endeavoring to elucidate the arrangement of the universe. Its primary and radical argument was, of course, that the sun was the center of the universe, but it also argued for other controversial points. Copernicus rejected the idea that the planets were fixed and unmoving bodies in space. Rather, he argued the planets revolve around the sun, and as they do so, they revolve in circular orbits. Copernicus's work was immediately rejected by papal authorities and criticized in Lutheran circles as well, including by Martin Luther. In 1660, the papacy added On the Revolution of the Celestial Spheres to the Index of Forbidden Books, banning its reading and study among devout Catholics. Despite the controversy, Copernicus had taken a major step forward in giving Europeans a truthful understanding of the structure of the universe. It would take many more decades to come in order for Copernicus's heliocentric view to be fully vindicated. The vindication of Copernicus probably began with the work of the Danish astronomer Tycho Brahe. Brahe spent a vast number of years laboring in his observatory, tracking the position and movements of planets and comets. He was probably the first scientist to rigorously base his conclusions on extensive scientific observation and data. Indeed, his astronomical data is considered the most accurate of his time period. He too took up the question of the structure of the universe and paid particular attention to the nature and function of comets. Brahe's work was impressive, particularly because he was the last major scientist to work without the use of telescopes. Brahe worked to reconcile the Ptolemaic astronomy of the Greeks with Copernicus's heliocentrism. Brahe agreed with Copernicus that the moon orbited the Earth and the planets orbited the sun, but he departed from Copernicus in believing the sun orbited the Earth. Brahe's most significant contribution was the vast amounts of astronomical data he recorded, and he did science a profound favor in sharing and passing on his data to his most gifted student, Johannes Kepler. Johannes Kepler was a brilliant German astronomer, mathematician, astrologer, and natural philosopher. Kepler held a firm belief that the universe was created by God with an intelligible plan that could be discerned by humans through reason. "I am merely thinking God's thoughts after him," is a phrase often attributed to Kepler, and probably was a concise summary of his belief that as image bearers of God, man is able to recognize and understand God's creation. Although Tycho Brahe was very guarded with his astronomical data, he came to trust and respect Kepler and his theories. Using an abundance of Brahe's data, Kepler formulated 3 laws of planetary motion. The first law stated that the planets move not in perfect circles, but rather elliptical orbits. The sun is one focus of an ellipse and not at the center. The second law stated that the speed of a planet is greater closer to the sun, and speed decreases the greater the distance of the planet from the sun. The third law stated that planets with larger orbits revolve at a slower average velocity than those with smaller orbits. Kepler seems to have identified the existence and role of gravity in the universe with his famous expression, "There is a force in the earth which causes the moon to move." Kepler made an important contribution in marrying mathematics with astronomy, but for many church authorities, his laws were still just theories that could not be reconciled with the Bible and traditional medieval conceptions of the universe. Kepler's contributions, like Copernicus's, would take additional decades to be fully verified and vindicated, but nevertheless, Kepler was ahead of his time and essential to the scientific revolution. Galileo Galilei has been called the father of modern physics and the father of modern science. Galileo was one of the first scientists to declare the laws of nature are mathematical. In light of that proposition, he made original contributions to the study of motion and combining experimentation with mathematics. Galileo was an Italian astronomer, physicist, and engineer who resided in Pisa and then the Duchy of Florence. Galileo extensively studied a number of key phenomena in the field of physics, including velocity, gravity, relativity, inertia, and motion. Galileo was able to make new and innovative contributions to the field of astronomy after he developed and continued to improve his own telescope. Galileo continued to enhance the magnification of the scope and take unprecedented recordings. Aiming his telescope at the moon, Galileo was able to argue that the moon was composed of similar materials as the Earth. Previously, it was thought that the moon and other heavenly bodies were translucent bodies of light and not physical mass. Observing the moon's craters and surface, Galileo put such theories to rest and proved the density of the moon. Galileo discovered additional craters and mountains on other planets and moons, including those of Jupiter. Galileo also observed the Milky Way, sunspots, comets, and began to theorize regarding the nature of ocean tides. In 1610, Galileo published the short astronomical pamphlet, Starry Messenger. This pamphlet was one of the first astronomical works to be based on observations conducted with a telescope. The work also brought Copernicus's ideas of a heliocentric universe to the public for the first time. And the work got Galileo in trouble with the papacy and finally forced the church to move aggressively against the emerging heliocentric consensus. Galileo's conflict with the papacy finally came to a head in 1633 when he was prosecuted by the Papal Inquisition for promoting heresy. The church had declared the heliocentric view foolish and absurd in philosophy and banned writings such as Galileo's, which advocated for the viewpoint. Galileo was charged with heresy and forced to recant his errors. After doing so quite reluctantly, Galileo was sentenced to house arrest for the remainder of his life. There's a famous anecdote about Galileo at his trial, at the end of which he supposedly muttered under his breath, "And yet it moves," referring to his unchanging belief that the earth rotated around the sun. Indeed, Galileo held on to his heliocentrism for the remainder of his life. The Church endeavored to block the emerging consensus on the structure of the universe, but it was becoming increasingly difficult to do so. It would fall to the Englishman Isaac Newton to finally and convincingly prove the heliocentric view of the universe, as well as to finally pull together the important contributions each of his predecessors made and present them as a unified understanding of the nature of the universe. Without question, Isaac Newton is one of the most brilliant scientists of all time, and the contributions he made to physics and understanding the universe were held in such high esteem that his mechanical view of the universe would dominate Western thought for the next 200 years and inspire a multitude of other philosophers and scientists to use their similar approaches in their respective fields. Newton was a mathematician, physicist, astronomer, alchemist, philosopher, and theologian. Newton became the darling of Enlightenment philosophers in the next century who generously applied his systems on a variety of fields of knowledge. Isaac Newton published his combined research regarding the mathematics and physics of the universe in his seminal work, The Principia, in 1687. The Principia is the last major scientific work to be published in Latin in world history. Newton explicated his 3 laws of universal gravitation in the work, laws of motion that would barely be challenged for 200 years and were fundamental to the coming of the Industrial Revolution in the 19th century. Newton proved the veracity of Kepler's laws and was the first to elucidate the law of universal gravitation. The Principia helped to explain planetary motion, tidal conditions, the trajectories of comets, the precession of the equinoxes, and the nature of the Earth as an oblate sphere. Like Kepler, Newton proposed 3 laws regarding the physics of the universe. Newton's first law stated, every object remains in a state of rest or straight motion unless acted upon by another force. The force could be friction, air, or a surface, but in a pure vacuum, an object continues to remain in motion. Newton's second law stated that the rate of change of motion of an object is proportional to the force acting on it. For example, the greater obstructive force, whether it be friction or something else, will more significantly reduce an object's motion. Newton's third law stated that for every action, there is always an equal and opposite reaction. In other words, forces result from interactions with each other. Newton's 3 laws became the basis of the mechanical physics that would dominate the field until the emergence of relativity theory in the 20th century. Newton also conducted extensive experiments in the field of light and color. He published his findings in 1704 in his work, Optics. In Optics, he developed a sophisticated theory of color based on his observation that a prism separates white light into the colors of the visible spectrum. Newton demonstrated that color arises from a physical property of light. Each hue is refracted at a characteristic angle by a prism or lens. Color is not inherent to an object, or even to light itself. Color is a sensation the mind receives due to the light's interplay with the lens of the eye. Color is a property of light, and not an object. Newton became president of the Royal Society in 1703 and was knighted by Queen Anne in 1705. Newton also served as professor of mathematics and a member of Parliament. During his lifetime, Newton never married, sired children, and had few friends. He performed most of his work in seclusion and lived alone. Newton believed God was the intelligent designer who had constructed the universe according to his natural laws, and once commented that he felt like a little boy playing on the seashore, while the whole vast ocean lay before him. While Newton's anti-Trinitarian views, if made public, would have had him labeled as a heretic, he did hold a high reverence for the scriptures. He experimented extensively with alchemy and endeavored to discern alchemic solutions hidden in the book of Revelation. Newton also exposed counterfeiting as the master of the mint and developed calculus simultaneously as Gottfried Leibniz in Germany. Newton would become the gold standard by which many subsequent mathematicians and scientists would judge themselves. Unfortunately, quite often found in Newton's shadow is the brilliant German mathematician, physicist, and philosopher Gottfried Wilhelm Leibniz. Leibniz, too, was a polymath, a brilliant pioneer in a multitude of fields, including mathematics, physics, philosophy, politics, law, history, and theology. Leibniz also anticipated much of what would later be confirmed in the fields of probability theory, biology, medicine, geology, psychology, and linguistics. The library cataloging system he developed for a library in Germany became the standard for library science across Europe. Leibniz's greatest mathematical contribution was the development of differential and integral calculus, apart from the contemporaneous work of Isaac Newton. Both Newton and Leibniz are considered founders of calculus, but subsequent mathematicians have come to prefer Leibniz's form of notation over that of Newton's. Leibniz was also a pioneer in the development of mechanical calculators, developing a series of different automatic adding machines. The stepped reckoner, also known as Leibniz calculator, was a digital mechanical calculator Leibniz invented around 1672 and completed in 1694. Because he also refined the binary number system, Leibniz is often considered the founder of computer science. Leibniz composed his letters and papers in several languages, including Latin, French, German, English, Italian, and Dutch. He was a devout Protestant and believed strongly in the Trinity until his death. Leibniz was a premier rationalist and believer in logical and mathematical explanations for questions of faith and philosophy. The field of medicine, which had been so slow to improve over the course of the Middle Ages, experienced significant development as well during the scientific revolution. Medieval conceptions of medicine and healing were often dominated by superstitious and ignorant assumptions that assigned little scientific thinking to ailments and cures. Sickness and pathology was actually frequently induced by the unsanitary conditions of the medieval world, and the cures for these ailments could be even more debilitating than the pathologies themselves. The most important development regarding medicine during the scientific revolution was a movement towards an organic understanding of pathology and a commensurate mitigation to address the ailment. Medicine and pharmaceutical solutions were not drastically improved by the end of the 17th century, but the groundwork for future developments were definitely installed during this time period. One of the individuals responsible for contributing to a medical revolution at the beginning of the early modern period was Theophrastus von Hohenheim, who frequently wrote under the pseudonym Paracelsus. Although an extraordinarily difficult man to work with and relate to, Paracelsus made a significant contribution to the development of modern medicine. Whereas Greek medicine, descending from the theories of the Greek physician Galen, emphasized balancing what he believed to be the basic structures of the body, Paracelsus assigned greater belief in the power of the appropriate treatment to heal illness. Whereas many medicinal remedies were randomly mixed together containing a multitude of natural poisons to the human body and thus inflicting greater illness, Paracelsus and his followers advocated for the combining, separating, and recombining of substances to produce the right remedy, thus retaining the helpful elements of a substance while reducing the toxins. Paracelsus was also an earlier advocate of the principle, like treats like. Rather than seeing pathogens as only an opposing cause of sickness, he argued the right amount of pathogen or the appropriate application could actually treat disease. Without knowing so, Paracelsus actually flirted with an understanding of the body's immune system. Andreas Vesalius made an even more significant contribution to the medical revolution of the early modern period. Vesalius, who was born in Brussels, became a chair of medicine and anatomy at the University of Padua and also served as the court physician for Emperor Charles V of the Habsburg Empire. Vesalius became a prominent critic of the theories of the Greek philosopher Galen, whose ideas dominated so much of European medicine. Vesalius was particularly unnerved that many of Galen's conclusions had been formulated through animal dissection, rather than working specifically with human corpses and human anatomy. Andreas Vesalius actually conducted autopsy on human cadavers and vastly expanded European knowledge of human anatomy. Andreas Vesalius actually conducted autopsies on human cadavers and vastly expanded European knowledge of human anatomy. Vesalius advanced medicine by propagating the idea that the body is a three-dimensional space with organs that work in tandem and particularly is not influenced by astrology or superstition. His public dissections attracted a great deal of public interest, and his research into human cadavers overturned an abundance of popularly accepted maxims originally offered by Galen. Vesalius published his groundbreaking on the fabric of the human body in 1543. In his work, Vesalius argued the skeleton was the framework of the human body, provided exceptionally detailed depictions of muscles and explanations on their function, elucidated the functions of the heart, arteries, veins, and nerves, and suggested a multitude of cures for chronic diseases. Vesalius was the first researcher to provide detailed descriptions of bones, organs, and make some connections on how the body worked together with its component parts. Future researchers would rely heavily on his groundbreaking 3D drawings and depictions of the human body. William Harvey was an English physician who also made important contributions to the development of medicine in the 17th century. Harvey offered the first comprehensive understanding of the circulatory system, including the observation that the heart is a pump and that blood circulates in the body. Harvey made a detailed analysis of the overall structure of the heart, going on to an analysis of the arteries, showing how their pulsation depends upon the contraction of the left ventricle, while the contraction of the right ventricle propels its charge of blood into the pulmonary artery. He noticed that the two ventricles move together almost simultaneously and not independently, like had been thought by his predecessors. Harvey challenged Galen's traditional assumption that blood was created in the liver. Harvey asserted that blood was produced in the heart, and he demonstrated how the blood circulated by means of countless experiments initially done on serpents and fish, and then later on humans. By tying veins and arteries in separate periods of time, Harvey noticed that modifications occurred. Indeed, as he tied the veins, the heart would become empty, while as he did the same to the arteries, the organ would swell up. Understanding that the heart was a pump and that the blood circulates in the body would have massive implications for the improvement of medical science in the centuries to come. The French physician Pierre Fauchard has been called the father of modern dentistry. Fauchard was one of the first physicians to describe the anatomy and function of teeth accurately. He explained how to identify the symptoms of oral pathology, methods to remove decaying teeth, means to restore teeth, early orthodontic care, and the replacement of missing teeth. He is credited with developing dental prosthesis and an early form of braces to correct the positioning of teeth. Fauchard denounced the medical quackery that often impaired dental science, often calling out the dangers of some common practices. Fauchard advocated for more reasonable means to promote oral hygiene and less barbaric means to remove decayed teeth. The field of chemistry also experienced significant development during the scientific revolution of the 17th century. Perhaps the most significant development in the chemical sciences during this time was separating this field from its usual associations with magic and alchemy. Popular understandings of chemicals and reactions had been so primitive during the medieval period that any step in the direction of conceiving chemicals as atoms, molecules, and reactions would be a significant advancement. Besides medieval superstitions and beliefs in angels and demons, much of the study of chemistry was hampered by the persistent pursuit of alchemy as a legitimate endeavor. Alchemy was the endeavor to transform one substance into another, or one element into another. The chief quest of the alchemist was to transform an inferior element, such as lead, into a higher element, such as gold. While chemistry, too, is concerned with reactions and the transformation of substances, the primary difference is the attention modern chemists place on the scientific method, verifiable laboratory experiments, quantifiable data, and the accuracy of experimentation. It was not until the 17th century that chemistry was gradually able to sever itself from the less reliable efforts of the traditional chemist. The Anglo-Irish chemist Robert Boyle was most responsible for separating alchemy from the emerging field of chemistry. Boyle was interested less in transforming substances as an alchemist and more in studying the natural active properties of substances and identifying the natural laws to which chemicals conformed. At Oxford, Boyle formed conclusions regarding air and its relationship to sound, the expansive force of freezing water, specific gravities, refractive powers, crystals, color, electricity, and hydrostatics. Boyle is probably best known for his articulation of the chemical law named after himself, Boyle's law. The volume of a gas varies with the pressure exerted upon it. Boyle was an ardent believer that the study of science could prove the truth of Christianity and provide evidence of God as the creator of the world. He was extensively involved in supporting missionary efforts to India and the translation of the Bible into local vernaculars. Boyle composed one of the most significant and early textbooks on chemistry when he published The Skeptical Chemist in 1661. In his seminal work, Boyle advanced his hypothesis that every phenomenon is the result of particles colliding in motion. Boyle asserted the primacy of experimentation in the chemical sciences and argued that chemistry was a science equal to physics, biology, and medicine. The Skeptical Chemist was the first major work to elucidate atoms, molecules, and chemical reactions. The French chemist Antoine Lavoisier has been nicknamed the founder of modern chemistry. Lavoisier's chief contribution was to transform chemistry from a qualitative science to a quantitative science. He placed additional emphasis on precision, measurement, and accuracy in experimentation. Lavoisier was the first to recognize and name oxygen, as well as hydrogen. He helped to develop the metric system and also composed the first list of chemical elements. Lavoisier's brilliant career, however, was cut short when he was guillotined during the French Revolution's reign of terror in 1794. Biological sciences received less attention, or at least experienced fewer developments during the scientific revolution. But in this field as well, scientific groundwork was laid that would become of great importance in the coming centuries. The magnification that a microscope provides was only slowly being developed in the century, and thus an understanding of microbiology was only just beginning. Robert Hooke was an Englishman and member of the Royal Society who gave increased interest to the study of life and organisms. Hooke was a polymath, interested in researching a multitude of fields including physics and chemistry, but he pioneered some important work early in the field of biology. Robert Hooke was the first scientist to view a microorganism through a microscope. In his major work, Micrographia, Hooke included illustrations of insects and plants that he viewed through microscopes. It was the first book to present such images. Hooke coined the cell to describe the basic unit of life, because when he viewed plant cells, they reminded him of the walled cells of a honeycomb. Readers were fascinated by the precise drawings, many of which folded out of the book to be double and 4 times the size of the standard page. Micrographia became an enormously popular book and brought newfound respect and attention to the Royal Society itself. Antony van Leeuwenhoek was a Dutch scientist and is considered a chief pioneer of microbiology and the use of the microscope. Leeuwenhoek was self-educated and is credited with establishing microbiology as a unique scientific discipline. He has thus been named the father of microbiology. Leeuwenhoek was the first to examine under a microscope and conduct experiments with microbes, particularly single-cell organisms. He was also the first to observe muscle fibers, bacteria, and red blood cells, and see blood flow in capillaries. Leeuwenhoek did not publish any of his books, but his extensive letters were published by the Royal Society. He constructed a multitude of microscopes and perhaps increased magnification up to 500 times. He also introduced the staining of specimens in order to augment contrast when viewing them under magnification. Leeuwenhoek was a devout Calvinist who marveled at God's creatures, both great and small, and believed his discoveries further proved the wonders of creation. Women rarely wrote about science even into the 17th century, but 2 female researchers are worthy of note. Maria Merian was a Swiss naturalist and illustrator who was one of the first European naturalists to conduct direct observations of insects and record her observations. Merian raised her own silkworms and published a 2-volume work solely on caterpillars. Merian tracked the metamorphosis of 186 different insects. Merian also conducted an abundance of work with butterflies. Margaret Cavendish was an English duchess who pursued a multitude of writing and research projects. In the field of philosophy, where women were virtually unknown, Cavendish composed 6 different books. Cavendish published Observations upon Experimental Philosophy in 1666, endeavoring to explain phenomenon in the natural world. Inherent to the new science was a whole new view of the world, a new respect for scientific inquiry, and a complete shift in worldview away from the long-held medieval assumptions. 17th century scientists were as much interested in formulating a philosophy of science as they were in conducting scientific experiments. They wanted to understand what they were doing and why they were doing it. The philosophy of science that prevailed during the 17th century was a firm belief in God as the original designer and creator of all nature. The very handprint of God could be found in the wonders of the natural world. Moreover, to make his universe self-sustaining and enduring, God had established natural laws to govern its functions. It was up to man to take up the task of discovering and understanding God's natural laws. An emphasis on natural law was foundational to the mechanical view of the universe as explained by Isaac Newton. Newton himself often used the word machine to describe the universe and its functions. The notion of the world as a great machine that operated according to fixed laws would dominate European conceptions of the universe throughout the Enlightenment and Industrial Revolution and not be unseated until the age of relativity in the early 20th century. The French philosopher and mathematician René Descartes contributed to the development of a rational and mechanistic universe. Descartes was a mathematician, philosopher, and scientist. He made significant contributions in a multitude of fields, including the development of analytical geometry. Enlightenment thinkers would eventually look back at Descartes as also one of the progenitors of their rationalist school of thought. Descartes theorized that man is a dualistic creature composed of mind and body. Descartes' willingness to separate the constituent natures of man, as well as his tendency to elevate the mind over the body, made him the darling of rationalists everywhere. Descartes arrived at his mind-body dualism through his philosophical method known as deductive reasoning. Descartes discussed deductive reasoning in his famous Discourse on Method, published in 1637. Deductive reasoning starts with a general premise, or two, and then forms inferences from the original and accepted premise. Descartes started his philosophical system by doubting the existence of everything unless it could be logically deduced. He concluded that God does exist because his mind could not conceive of a greater being than the concept of God. He concluded that he existed because he was capable of rational thought. His famous dictum was, cogito ergo sum, I think, therefore I am. From these general premises, Descartes would move on to deduce one logical inference after another. Cartesian logic would gain an even additional respect in the coming century during the Enlightenment, with its emphasis on reason and logic to prove anything. Sir Francis Bacon, too, was one of the prime contributors to the philosophical underpinnings of the scientific revolution. His emphasis on empiricism, research, and discovery through experience became a hallmark of modern science with its emphasis on reason and rationalism. Bacon explored the significance and nature of modern inventions such as the printing press, gunpowder, and the compass. He was also an advisor to Queen Elizabeth I and James I of England, and was knighted for his extraordinary works. But Bacon's most enduring contribution to scientific endeavor was his formulation of inductive reasoning. Bacon believed responsible scientific investigation would require the examination of evidence in small pieces, which in turn would enable the researcher to formulate more general conclusions and theses. Bacon elaborated on the importance and value of inductive reasoning in his work Novum Organum, which was part of his larger series, The Great Instauration, which envisioned a new birth or era in scientific investigation. Bacon believed that nature had been given to man for his use and dominion, and that its study would glorify God and fulfill the Scriptures. Descartes and Bacon both made essential contributions to the formulation of the scientific method. Bacon's inductive reasoning, which emphasized forming conclusions by going from the specific to the general, was essential to scientific inquiry through background research and the construction of hypotheses. Descartes' deductive reasoning, which emphasized moving from general conclusions to specific situations, was essential to scientific inquiry through the testing of hypotheses through experimentation and the analysis of data to form a conclusion. Isaac Newton is credited with combining these two approaches to develop the scientific method, an approach to scientific investigation that combines specific observations, data, and conclusions with general conclusions regarding natural law, and an approach that can be verified and repeated to ensure accuracy and precision. Beyond the mechanical philosophy of science and scientific method that researchers developed in the 17th century, however, was the question regarding how science intersected with the spiritual. What is the relationship between God and the natural world? What should be done if conclusions in the laboratory do not seem to agree with the teachings of Scripture? Thus, the scientific revolution raised questions not only about the philosophy of science, but also regarding the theology of science. Baruch Spinoza endeavored to answer these theological questions in a controversial manner for his time period. Baruch Spinoza was a Dutch Jew who advocated for a strict rationalism born in the age of science. A controversial figure during his lifetime, Spinoza was viewed with suspicion within Jewish and Christian circles. Although he did not advocate for atheism, many felt that his ideas were a step in that direction. Spinoza believed reason and rational thought could explain every problem and find every solution. His veneration of reason earned him the opprobrium of his contemporaries, but the respect of his intellectual descendants would also revere reason as the highest quest during the Enlightenment. Spinoza also advocated a controversial form of pantheism that closely equated God with the very substance of the universe. The scientific revolution, which generally still saw God as the creator and designer of nature, was not very receptive to Spinoza's ideas. His radical rationalism would find more acceptance in the following century, during the Age of Reason. The French philosopher and mathematician Blaise Pascal differed with Spinoza regarding the harmony of science and theology. Pascal emphasized the importance of faith alongside reason, God alongside the natural world, and the laboratory alongside the scriptures. For Pascal, there was not a great gulf between faith and science. Pascal was a pioneer in a multitude of fields. He too was a mathematician, physicist, inventor, philosopher, and theologian. From an early age, Pascal took great interest and made contributions to projective geometry, probability theory, economics, and social science. He is also considered one of the earliest inventors of the mechanical calculator. Pascal challenged his contemporaries by defending the scientific method and made important contributions regarding the nature of fluids and vacuums. Pascal experienced a dramatic conversion experience in 1654, and thereafter wrote more on theological topics than those of physics and mathematics. Pascal bore a strong affinity to the Jansenist tradition that was becoming increasingly popular during his lifetime. Jansenists bore strong resemblance to Calvinist doctrine, even as they remained in the Catholic Church. Pascal became a strident critic of the radical rationalism and empiricism that was beginning to take hold in Europe during the early Enlightenment, and rather argued for the primacy of faith as above that of reason and experience. Pascal's greatest work is Pensées, that is, Thoughts, which was published in 1670. Pensées is considered to be a masterpiece of French prose and widely revered even by Pascal's critics. Pensées was never finished and published after Pascal's death, but it seems to have been constructed as a broad defense of the Christian faith and a rejection of pure rationalism, hoping to drive the reader to despair and then to embrace faith in a living God. The implications and legacy of the 17th century scientific revolution were immense. Long-held medieval assumptions and ignorance about the natural world was abandoned. The scientist and the laboratory replaced the philosopher and the monastery as the true repository of scientific knowledge and understanding. The empiricism of the revolution went hand in hand with the Reformation's rejection of superstition. The scientific method showed the way forward for centuries to come on how to conduct responsible and accurate experiments. The rationalism and reason extolled during the Revolution would become the rallying cry and primary theme of the 18th century Enlightenment. Newton's mechanical view of the universe would be the predominant construct of reality for the next 200 years. The tinkering and inventing that occurred in the century would inspire additional inventors, leading to the Industrial Revolution. The explosion of scientific inquiry would lead to an extended and vigorous debate regarding the relationship between faith and science. For most researchers in the 17th century, however, there was little difficulty in reconciling the two. Most mathematicians, physicists, physicians, chemists, and biologists in the 17th century also considered themselves theologians. They were not examining phenomenon independent of the question of God's existence. They believed they were examining the very handiwork of God himself. This close relationship between faith and science was assumed and relished during the birth of modern science in the 17th century.